Hello and welcome to the last part of Chapter 13. So the first part of this installment or this podcast is going to be review. So we're going to review from Chemistry 20 titrations. So let's do a quick review. So a titration is a quantitative laboratory technique used to determine the concentration of an unknown solution. So this is what we did in Chem 20 to find the concentration of an unknown solution. A reagent of a known concentration called the titrant. Now that's sometimes the titrant, sometimes the sample, like depends on what you start with and what you're looking for, is used to react with a solution called the sample. Okay, the titrant is the thing that goes into the burette, and the sample is the solution that goes into the Erlenmeyer flask. Using a burette to add the titrant, the volume needed to reach the endpoint can be determined. The endpoint is where you have the color change, remember? It's when the color changed and it was permanent. The endpoint is the point at which the titration is complete, usually determined by an indicator, the color change, but not always. This is ideally the same volume as the equivalence endpoint. The equivalence endpoint speaks to the number of moles that have reacted between the titrant and the sample. When stoichiometry equivalent amounts of each reagent have been added, and that's talking about the number of moles. So this is your quantitative data, and the color change is your qualitative data. There's the example of a good endpoint is when you have the one single drop that's going to allow the color to change permanently. This obviously too much, right? Too much of the titrant was added to the sample. There's basically the apparatus. You guys remember that? Let's take a look at the titration procedure review. So you have an initial reading of the burette. Remember we looked at in the burette we used the meniscus to find the reading. You have the initial reading, and then the titrant is added until the reaction is complete. Remember, the reaction was complete when we had the color change. When a final drop of titrant permanently changes the color of the sample, and then we take a final burette reading. Once you take a look at your initial and your final, you subtract them to find the number of milliliters or the volume necessary for that reaction to occur. And recall that you needed to have 3 volumes that were within 0.2. You took those 3 and you averaged them out, remember? So here's the procedural review again. A titration should involve several trials. You need to really have 3 good data points. A typical requirement is to repeat titrations until 3 trials result in volumes within a range of 0.2. These 3 results are then averaged, and then you use that averaged amount as your volume. Remember about the meniscus, I talked about that. Remember to top the burette at around 0.0. If you have that luxury, it doesn't always have to be that way. So you will subtract the initial reading from the final reading to determine the difference of the amount of titrant needed. You don't always have to go to 0. You can just, at any point where you kind of ended is where you start the next trial. In a titration, one reagent, the titrant is slowly added to another of the sample until an abrupt change in solution or the endpoint occurs. In redox reactions, in redox titrations, I should say, the titrant is always a strong oxidizing or a strong reducing agent. So now we're taking a look at what the strong reducing agent, the strong oxidizing agent is. In a redox titration, another difference is there's no indicator. You don't add the indicator to your sample. It's not required. However, you still get a color change. Because a titrant is an SOA that has a very significant color change when it undergoes reduction. 2 oxidizing agents commonly used are acidic solutions of permanganate or dichromate ions. These are usually your examples because there is a color change associated with them. And there's just an example of what's going on. If you have, oops, dropped my pen. If you have the MnO4, you get a purple-pink color. If you have the Mn2 plus, you go colorless. So there's going to be a change in color anyways without the need of an indicator. And for the what is it? The dichromate ions, you have a color from orange to green or green to orange. So no need for an indicator. That's kind of cool. In a redox titration, it is often necessary to standardize a titrant. We're not doing that because we don't go to labs. Due to the reactive nature of the oxidizing agents used as a titrant, they often react with themselves in their storage container. You're not going to be tested on this, kiddos. All you need to know is how to use um, the strongest oxidizing agent, strongest reducing agent to make a net ionic equation, and then use your redox stoich. Well, I'll go over it. But this is just some background information. Standardizing involves performing an initial titration with the solution prepared from a solid so that you know the exact concentration to determine the exact concentration of the titrant. Awesome. Let's take a look at redox stoich. There are many industrial and laboratory applications for redox stoichiometry. An example is mining, a type of engineering that you need to know the concentration of iron in a sample of ore to decide whether or not a mine could be profitable. Chemical technicians must monitor the concentration of substances in products. Hospital lab techs must detect any tiny traces of chemicals in human samples. And how is this different from Chem 20? We will need to predict the redox reaction or equation that will occur, and then we will use the quantities provided to answer the question. The math is the same as Chem 20. We just need to be using our knowledge of redox to start the question to set it up. By the way, you are not going to be tested on this or this for that matter, just how to do the redox stoich. Okay, so here's an example. A strong acid, the first one I'm going to go through quite slowly, so I'm just going to. Okay, so a strong acid is painted onto a copper sheet to etch a design. If 500 milliliters of a 0.250 moles per liter solution is used, what mass of copper will react? So we're going to first list all your entities. You have copper solid. You have a strong acid. A strong acid, all you have to do is say this, hydronium ion for a strong acid. And you also have to know, I think that might be it actually for that. And of course, solution, right? Because a strong acid is in solution because it's aqueous. So one of the entities has to be water. You go ahead and list your entities and find your SOA and your SRA. And then you're going to write the oxidation and reduction half reactions. You're going to balance the number of electrons gained and lost. And then you're going to add these up. You're going to add these up. Then what's most important here is you're going to populate. So the volume is 500 milliliters. The concentration of the acid is 0.250 moles per liter. I'm looking for the mass. If I'm looking for the mass, anytime you're asked to find the mass, you include the molar mass of that substance. And then it's just much easier to actually do the stoich. Now let's compare the coefficients found here. And that becomes, this is a 1, that becomes your molar ratio of what you have to what you're looking for. So here we go. You always start, see over here for the strong acid, you have all the information that you need. You have your volume and your concentration. You start with your volume so that your liters cancel out. In this case here, I changed it to liters, right? 500 milliliters is equal to 0.50 liters so that the liters cancel out. If I'm looking for volume, I don't really have to worry about that if it's in milliliters because your answer will be in milliliters, but I'll show you an example. So this will cancel out, give your answer of moles of hydrogen. Obviously, remember from stoich, in your denominator you have the moles of what you have, and this is the coefficient of the moles of what you need. Okay, so I have the information for the hydrogen, so that cancels out, and then I want the information for the copper. That's why the 1, which is taken from here, goes there. And then I multiply by the molar mass so that the moles of copper cancel out and I get my answer in grams. This time the grams is on top so that the moles cancel out and you get your answer to 2 decimal places. That's fine. I'm not going to do significant digits or anything like that. Here's an example number 2. Just going to go over this. So nickel metal is oxidized to nickel 2 plus ions by an acidified potassium chromate, dichromate, sorry. Remember acidified, you have to have H plus, and H2O is always going to be a thing. If 2.5 grams of metal is oxidized by 50 milliliters solution, what is the concentration of the potassium dichromate solution? Let's list our entities and find our SOA and our SRA. Now in this case here, this is a combo, so you have to include both, right? But that's how it shows up in your data booklet, so not a big deal. And that's our strongest reducing agent. So write the oxidation and reduction half reactions, balance the number of electrons gained and lost in the reactions. So here's my net. I had to multiply this by 3 because here I have 6 electrons, here I only have 2. I have to multiply the 3 by everything so that your electrons match, so then we can cancel them out. Then we populate. This is, again, really important. We're populating. I have 2.50 grams of the nickel, and I have the molar mass of the nickel because I have grams. Anytime you have grams, you include the molar mass. I have my volume, and which is 50 milliliters or 0.05 liters, and I'm looking for my concentration. Now, remember, concentration is equal to number of moles over volume. You can, if you want to use your Stoich to get to the number of moles, then you can go ahead and use the C equals N over V, or at the very end, just make sure it's 1 over your volume. Okay, so let's start from the beginning, 2.5 grams of your nickel. I'm using this because, right, I have everything I need to get to moles. I use my molar mass. This time the grams are on the bottom so that the grams cancel out. Now I get moles of nickel. Now here I have my molar ratio. 3 moles of nickel is what I have. And I'm looking for what I need, and the coefficient for the chromate ions is 2. Now that's going to get me moles. All this information is going to get me moles. Right? It's going to get me moles of this chromium ions, right? So I don't want moles, I want concentration. That's why there's a 1 here. There's a 1 there because I want moles here. It's moles per liter, right? And if you get to here and you find the moles, you can definitely use this. If you don't remember it's 1 over the volume, go ahead and use C equals N over V. And you get an answer of 0.57 moles per liter. So here's another way, and that's by using a table. So a solution of potassium permanganate cannot be directly prepared with a precisely known concentration because the permanganate ion reacts with organic and inorganic impurities in the water and with the water itself. Thus, potassium permanganate is not used as a primary standard. Complete the analysis of the investigation report. Okay, a lot of information. All we're really looking for is the volume of something. So the problem, what is the concentration of, we're looking for the concentration of the potassium permanganate solution. We're looking for the solution, kiddos. The solution is the whole thing. So here's our design. Design is just basically the experiment. A freshly prepared solution of potassium permanganate is titrated against samples of acidic tin. So we have acidic, right, H plus, tin 2 chloride solution, which has a known concentration. The tin 2 chloride solution is the primary standard. Awesome. So here's your information. I have 10 mils of the acidified amount of your tin 2 chloride with potassium permanganate. So these two bits of data points belong to here. And I'm using the chart to look for the volume of your potassium permanganate solution. I'm going to use a chart. So you have your final and your initial where you're going to subtract these two numbers, subtract these two to get your volume. Now notice that you have 17.4 dark pink. Dark pink is telling you maybe not such a great titration. Light pink, light pink, light pink, and 16.9, 16.7, and 16.8. The 3 of these are within 0.2 mils. So essentially, essentially, we don't use this one. We take these 3 and what do we do, guys? We add them together, divide by 3 to get your volume. So list all your entities, decide what your SOA is and what your SRA is. Okay, this is your strongest reducing agent. Your strongest oxidizing agent is a combo. And this is a typical one, right? So then I just have to make sure that my electrons balance. I have 5 here, 2 here. The lowest common multiple is 10. So that's where this 2 came from and this 5 came from. You know this. That's going to cancel out my electrons. Here is my net. Then once I have this guy, I just go ahead and populate it. So I have 10 milliliters at 0.05 moles per liter of your tin ions, tin 2 ions, tin 2, 2 plus. I have my volume. This was taken from the chart. And I'm looking for my concentration, which is in moles per liter. Now notice that this is in milliliters and this is in milliliters. I actually don't have to change it to liters because they'll cancel out. So here we go. I'm starting with my 10 mils, and there is my concentration, moles per liter. Here's my molar ratio of my tin and my permanganate. Now see my milliliters? This is where my milliliters cancel out. And then I am left with liters and moles. So then I just use my trusty calculator and I get my 0.0119 moles per liter. And that's it, kiddos. So good luck with this. I am also including a practice, I think it's 6 questions, along with a key. So good luck, and you guys have your formative coming up, and then I'll post the annotated formative key. It's color coded, so that was really fun for me. And have a